Another day, another story. The question of whether light is a wave or a particle has baffled physicists since the 17th century. The problem first emerged when Isaac Newton developed his corpuscle theory, which described particles of light that must only travel in straight lines, as seen in the reflection in a mirror. At the same time, other physicists, including Christiaan Huygens and Thomas Young, proposed that light must propagate as a wave, displaying properties like diffraction and interference. In fact, neither of these theories is necessarily wrong, as both are consistent with experimental observations when the right context is applied. On quantum scales, light travels in packets called photons, but it also reliably follows Maxwell's equations, describing the dynamics of classical electromagnetic waves. To explain how both theories can be correct, physicists needed a way to unify classical electrodynamics and quantum physics into a deeper, all-encompassing theory, known as quantum electrodynamics. Generalizing classical physics, around the beginning of the 20th century, several physicists began working on revolutionary theories to explain why matter behaves differently on extremely small scales. The resulting field of quantum mechanics resolved many questions that classical physics couldn't answer. Quantum theory is a generalized theory, with classical physics being just one specialized branch. While physics may appear non-classical on quantum scales, classical behaviors emerge on larger scales, where quantum processes become less relevant. Quantum mechanics unites explanations for physical behaviors observed on various scales. But even quantum mechanics is not general enough to explain all observed physics. The incompleteness of gravity, first described by Newton, can be accurately described in many situations using classical physics alone. However, these theories can't fully explain all phenomena observed by astronomers. Albert Einstein's theory of general relativity resolved this issue by generalizing gravity into a geometric model, uniting space and time into space-time. Einstein's theory, though successful, appears incompatible with quantum mechanics, necessitating a deeper generalization known as quantum gravity. Dr. Sanchez aims to realize this theory, incorporating physical theories developed since Einstein's equations. Dr. Sanchez's approach starts from quantum theory and extends it to high-energy scales where gravity and quantum effects are equally important. This semi-classical gravity acts as a bridge between quantum mechanics and general relativity, contributing to a unified theory of quantum gravity. Extending classical quantum duality, Dr. Sanchez brings semi-classical gravity to quantum scales. She explores how gravity could work in this regime, unifying three fundamental physical constants: Planck's constant from quantum mechanics, Newton's gravitational constant from classical gravitation, and the constant speed of light from general relativity. Dr. Sanchez's theory introduces wave-particle gravity, duality, or classical quantum gravity, duality. This theory suggests that both wave-like and particle-like behavior of light are branches of a more deeply rooted theory. Dr. Sanchez's universal theory reveals that wave-particle duality of quantum physics is a special case, not a general rule. This theory allows for the emergence of properties like the classical quantum duality of spacetime, previously elusive. Additionally, it unveils a new quantum domain not present in the classical description of spacetime, providing a more complete understanding of its properties. One significant result of Dr. Sanchez's theory is the emergence of a quantum light cone, which doesn't appear in classical descriptions of the universe. This quantum light cone includes a space between opposite-facing hyperbola-shaped cones, where quantum properties emerge, surrounding a flash in time and space. On larger scales, the classical light cone re-emerges, harmonizing previous theories. Applying her theory to black holes, Dr. Sanchez reveals that their outer regions are classical or semi-classical, while their interiors are governed by quantum mechanics. A quantum border emerges where the event horizon disappears, unifying the interior and exterior on quantum scales and avoiding the classical spacetime singularity. This transformation in understanding suggests that the physical and universal wave-particle duality of quantum physics holds the key to solving quantum gravity. It has the potential to revolutionize our understanding of astronomical scale phenomena, paving the way for an exciting new era in theoretical physics and cosmology. Thanks for watching.